Hello everyone. I would like to share my latest work on Scoop, Mitigation of Recapture attacks on Provenance-Based media authentication. This is a joint work with my colleagues Habiba, Ardalan, Jane from UC Irvine, and our collaborator Sharad from Microsoft. Let's get started. Today, we live in a digital world, and with the help of all these social media platforms, information spreads really fast. Unfortunately, that also applies to fake and fraudulent information, which is especially true with recent advances in both deepfake and generative AI. In the past, there have been some detection-based approaches trying to counter those fake and fraudulent information, but they seem to be more like an endless race that's unlikely to win. Recently, there has been something new called provenance-based media authentication that has been on the surface. What provenance is, it is essentially a cryptographic proof for the visual content. Let's say we have a provenance-enabled smartphone camera. Whenever it captures some visual content, we will generate a provenance along with the content. And then whenever the content gets updated during process such as post-processing, the provenance will also get updated to record the history of everything about the content. And then there might be some more updates for the content and provenance information during processes such as publishing sharing platform. And then finally, the viewer can look into the provenance information and then to authenticate the content. And there has been some academia effort, including my previous lines of work, such as ProfCam and Veronica. There's also a huge amount of effort by the industry, like Content Authenticity Initiative and C2PA, where Content Authenticity Initiative is a joint effort by many big names in the industry, such as Adobe, Microsoft, and so on. So, with this provenance-enabled system, are we safe now? Well, absolutely no. And here comes challenge number one, where provenance only authenticates the origin and history of the content, but not the information within the content. What does that mean? Well, today I would like to shed light on something called recapture attack in this provenance area. Let's say I'm a facility manager at my school, and I'm responsible for making sure all fire cabinets within my school are in good shape, and I need to take photos and upload them with my provenance-enabled camera. One day I happened to find this empty fire cabinet. Or by being too lazy, I don't want to deal with this matter, I don't want to deal with the school, I don't want to deal with the missing fire extinguisher. So, after taking a photo of it, I put it on my desktop, and using some generative AI magic, I put a fire extinguisher into this fire cabinet. Then, I took my provenance-enabled camera out, and I took a photo of my screen, without having the frame of the screen included in the photo. And now I have a photo which is showing this fire cabinet, and there is a fire extinguisher within it. And this photo is authenticated by the provenance information generated by this provenance-enabled smartphone. This is relatively a benign scenario, where think about that there could be more dangerous ones, such as the use of insurance scamming, where people can arbitrarily create some accidents and then claim for insurance. Recapture attack is not really new, but it is getting renewed. First, it is easier to do content manipulation and fabrication thanks to deepfake, where we can do face swap. Second, it is simpler to create illusion of reality, which is true with the advancements of displays, such as this bus, where it has no windows, where all those windows, or those look like windows, they're actually just displays. Third, which is also the most important point, with the widespreading or introduction of provenance-based system, people are going to start to have false sense of trust towards all content that have provenance. So, provenance recapture attack is not new. Then, are there any existing countermeasures? Well, there are. Broadly speaking, there are mainly two types of recapture attacks: screen-based and print-based, where we found that the majority of those countermeasures for both of them are focusing on getting a really tiny detailed pattern that exists in the recapture medium. Do those countermeasures work? Well, not really. That is actually due to the point that they are trying to catch those detailed pattern, which makes them depend on prior knowledge of the recapture medium and the camera. And just a reminder here, attackers are in control, where they can do whatever they want to both recapture medium and the camera. I won't get into too much details of how the attackers can do this, but some fellow researchers have already published a paper at the same conference of us, USENIX Security 2025. And they clearly show that how attackers can bypass those image recapture detections. So some of you might not wonder that, okay, I know that machines cannot do it. Machines cannot detect recaptures, but I'm built differently. Well, that's why we conducted a user study, where we took a total of 16 photos. 8 of them are original and 8 of them are recaptured. We recruited a total of 43 adult participants, and all of our user studies are done on a single laptop. The result is quite unsurprising, where we have a average correct classification rate towards all participants right at about 50%, which is, as you guessed, is pure randomness. So, how do we tackle such attack then? Well, we now know that aftermath analysis-based approaches are again an endless race that's unlikely to win. And we think that provenance can still help here. That's why we would like to advocate for something called depth-enabled provenance, where we essentially want to make use of something called time-of-flight depth sensors, including both direct time-of-flight and indirect time-of-flight. What they do is they measure the absolute distance to a target from the camera, and they are equipped on modern smartphones. With this depth-enabled provenance, let's not look back on this fair cabinet example. And with the help of depth provenance, we can recreate a 3D point cloud of this photo. And as you can see here, it is a flat surface, which doesn't really align with what we have in mind for this photo. So, problem solved. We can just simply flag all flat surfaces as recaptures, right? Well, we're not there yet. And here comes challenge number 2, where not all flat surfaces are recaptures. Let's take an example of this wall, where again we have a photo of this wall with depth-enabled provenance. And we again recreated a 3D point cloud using the depth provenance. And as you can see here, well, they're both flat. But it is fine for a wall to be flat. That doesn't mean that this is a recapture photo. So what we want here is we only want to catch those real recaptures. And how about we compare human perceptual depths with provenance depths? Whenever we agree with each other, then great. But whenever we disagree with the provenance depths, then, well, there must be something wrong. Apparently, we can't really compare that human perceptual depths with provenance depths every single time we look at a photo or a video frame, and that's why we leverage learning-based molecular depth estimation algorithm, where we use it to estimate human perceptual depths. Introducing Scoop, where it takes a visual content with depth-enabled provenance, it then highlights those regions that it thinks that it is having some recapture going on within those regions. In Scoop, it takes a digital content with provenance information. Well, it has to be depth enabled, and then using just the RGB content of the digital content, we can use depth estimation algorithm to generate a learning-based point cloud. We can also generate a ground truth point cloud using just the depth-enabled provenance. We will then do regional segmentation, regional comparison, and then finally, we can highlight those regions that they disagree with each other. So I won't get into any technical details of Scoop, but if you're interested, please feel free to go read our paper. And now let's see Scoop in action, again with this Farrukh cabinet example. We first generated the 2 point clouds, one learning-based and one ground truth-based. Then we compare those 2 point clouds, where as you can see here, we're clearly seeing some regions that they disagree with each other. Then we can just simply highlight those regions. One thing I would like to remind here is those are just really high-level concept. They don't really mean the actual accurate technical concept or technical implementation of Scoop. Please refer to our paper for the actual technical details. Then let's take a look on this wall photo, where we then generate the 2 point clouds, a learning base, the ground truth base, and then we do comparison between them, and there's no region that they disagree with each other, so there's nothing we need to highlight. Now let's take a look on a new example, where we generate the 2 point clouds, and then we compare them. As you can see, the ground truth one is having a little bit flat surface for the human shape, where, well, we need to highlight that region because they disagree with each other. And what this photo is showing is that it is a life-size cardboard cutout of a human being. So for the prototypes, we have built a desktop viewer application, an iOS camera application, and an Android camera application. Using those 2 camera applications, we can capture any any visual content, both video and photos, and then we can view it with the visual content captured by those 2 camera applications, as they contain the needed depth provenance information. As for the evaluation, well, that is also the third challenge, where we found out that there's no existing dataset that is designed for evaluating systems like Scoop. That's why we also captured a first-of-its-kind dataset using our 2 smartphone prototypes, where we captured a total of 122 unique data points, including 78 recapture scenarios, where we make use of TVs, cardboard cutouts, projectors, or mixed scenarios. And we have captured both photos and videos. We believe that this dataset is setting up a cornerstone for evaluating systems such as Scoop. As for the effectiveness, well, with the dataset, we can finally evaluate our prototypes. And for the true positive rate of our prototypes, which means that they correctly identify any misleading recaptures, both iOS and Android-based prototypes are achieving relatively high true positive rates. As for the false positive rate, where they incorrectly identify benign photos as recaptures, both iOS and Android-based prototypes are again achieving relatively low false positive rate. As for the overhead, which you can see here, for both runtime and storage, we are actually incurring some amount of overhead. Where one thing I would like to clarify here is that for our prototypes, it is more of a proof of concept, where we want to show that our system is doable. It is not really optimized for performance at all. For example, we are only using a single CPU thread for all kinds of computation, where we can for sure offload those computation to either multi-CPU threading or GPU computation. As for the storage, well, we can make use of some lower depth resolution for the depth provenance. Whereas we have evaluated in the paper, even having lower depth resolution, it is not going to affect our system performance too much, which you can refer to our paper for more detailed evaluation of our system. In summary, we shed light on an important vulnerability in existing provenance-based techniques. We introduced design of scoop, which is an effective countermeasure against recapture attacks. We have also captured a first-of-its-kind dataset that is just designed for evaluating systems like scoop. We have also built a fully functional scoop prototype based on just commodity devices. That will be the end of my presentation. Thank you very much. And please feel free to go read our paper, and our prototypes are fully open source. Please feel free to go check out the codes. And if you get any questions, also feel free to email to me. Thank you very much.